In this video, we're going to implement a private voting system where anyone can vote without revealing their identity, and we can actually tell what they voted for. And we're going to deploy all of this to Midnight Network. Midnight is a privacy-first blockchain that blends public verifiability with confidential data handling, right? If you want to go into all the needs and details of this, assuming that this is your first time with Midnight, go to the documentation. Just open midnight.network and the developer options right here, you will find and see all of this documentation. But for this tutorial, we're focused on writing a smart contract for Midnight. So we're going to dive into the dips, and during the course of that, we're going to attempt to walk through the code step by step for you to understand what's going on. All right, so now that we've gotten that out of the way, the first thing we need to do is set up our environment. You've probably never written a smart contract for Midnight, and you probably don't even know what's going on. For Midnight Network, the smart contract programming language used is called Compact. Compact is a programming language, same as you have Solidity for Ethereum and you have JavaScript for web applications and all of that. Compact is a smart contract language for Midnight. It has some new interesting types and features. So like I said, if you go to Midnight Network and you go to developers, go to docs, you will see this beautiful, wonderful docs right here. It's going to walk us through everything we need, right? What is Midnight? Can eat all of this really, really interesting technology right here. What we're looking for is called installation. This is going to set up us. With this, we're going to set up our environment to start writing smart contracts. And the first thing we need to do is install Compact. Compact is Midnight's dedicated smart contract language for creating the applications, decentralized applications that allow developers to control the level of data protection in their applications. Compact is built for reveal what you want to reveal, hide what you want to hide. So to install the binaries and everything that needs to compile the code, you just copy this, you open your terminal and you paste it, right? Paste it right there. For example, I'm just going to paste this. Did I copy it? I'm just going to copy this, head over to my terminal, paste it. When I smash enter, it's going to install all of that. And we should have that set up. I currently have it installed. So let me show you how I know. If I just run Compact, version, once you get back a number right here, that means you've successfully installed the compiler, the binaries that is needed to compile the code. Another thing you need to actually have on your PC before you, in the process of setting this up, is to install Docker, right? We need Docker to run the proof server, right? To run the proof server, we need Docker. So you install Docker Desktop, and once you just go to Google, just search for Docker Desktop. The first link should get you to install it. Just install whichever application that your operating system uses. Okay, so setup, I think we're pretty good. Once you install all of that, that is done. Then you also need to install the VS Code extension. It's very important, right? Once you get to that, you will see why it's important, because you want all those color highlights and all the the VSIX package. You're going to install that. This is right here. Just install it. And that sort of like concludes the setup. That's how fast and clean it is, right? Once you do all of that, you are pretty good to go. You can follow this in detail, but those are the highlights of everything. You install the Compact binaries, you install Docker, you can download all of this, but with the way we're going to write this code today, you might not need to do any of these other parts, just this part. Okay, now that we got the setup out of the way, by this time, hopefully you've installed Compact, you've installed everything. Let's go into actually creating the smart contract we need to write. For today, I want to take a stab at what we are trying to build. We want to build a private voting system, right? We have a system where there are going to be two options. There are going to be two options. Just put it right here. We have a yes. We have a no. Did I get that? We have a no, right? And we have a voter. So let's represent that with a very interesting circle. So this is a voter. This is probably you. And we have multiple voters, in the country. We want each of them to enter the voting booth and vote, but we don't want to reveal what they are voting for or who the voter is. And that's what we're trying to build. I don't understand what I was trying to achieve with this image, but hopefully that makes sense, right? We have the voting booth, we have the voting box, but we want them to be able to vote, but we don't want to know who is voting for what. We want to just see, oh, Somebody voted for yes, somebody voted for no. We don't want to see the identity of the voters. And Midnight is a very interesting blockchain, very capable of handling this nuance that comes with data protection and data visibility, is what I'm trying to say. Okay. All right. So let's get to writing. We can start from scratch and start writing our smart contract and set everything up. However, I would advise that you actually clone a startup project and tweak what you need. The reason is that Midnight is still in the process of becoming the most stable version of itself. It's in beta, alpha, or whatever stage it is currently. So a lot of things are changing really fast. And the way you can just save yourself a lot of stress and trouble is to just start with a startup project. This is one by a DevRel at Midnight. Once I just clone this, we'll have a base project to work with. So I will just go right here. And then inside here, I'm going to do the clone. I'm going to paste this and call this private voting system YouTube. You can call it whatever you want. I'm calling the private voting system because I feel like it just makes sense to me that way. Then I'm going to open this in my coding editor of choice. I love Cursor. I use Cursor. In fact, I recommend you go to Cursor, but that's out of what we're trying to discuss in this. What's more important is just open it in something they're comfortable with. And I recommend Cursor if you want to do something with AI and help you use AI. And in fact, now that I mentioned AI, you can actually install the Midnight MCP. Now, this is one singular thing that you can install you can set up in your project that will 10x the amount of speed and comfort you will get from writing Midnight contracts. It really is a game changer. And I'm just going to add all of these links to the description of the video, so don't worry about it. If you go to this URL, which I'm going to add, or you can search on GitHub, just come down right here. I think I submitted a PR some time ago. And if you look for Cursor, like I said, get Cursor. And you just click on this button. Once you click on this button, it's going to actually install Cursor for you it's going to install this MCP, in your coding editor. Really straightforward, to the point, right? Set this up so you can use AI, because this does a number of interesting things. It can compile your code for you, can write code for you, can search the documentation for you, and gives context grounding to your AI, and not just hallucinate, because Midnight is pretty new, so not a lot of things are standard yet. Very important that you add this. So add this is very important if you want to use AI for anything. So let's go back to our project. I think I have mine here. I'm just going to switch to the appropriate view. Boom, something familiar that we recognize. I'm going to make this bigger a bit, and then I'm going to close this. Okay, so now that we have this, let's go to the README. I think the README will set us up. Right, in the README, we need to do npm install. By the way, this is the project we just cloned. Don't forget that. So we need to do npm install. So I'm just going to do npm install. So npm install is going to install all the, things that we need in this smart contract project. Everything we need for Midnight, all the packages that Midnight needs, and everything. I'm just going to get it installed in this bundle and everything. So next thing we can compile. Let's actually compile what is currently there. And let's see. The compilation, okay. Missing public parameters for all of this. Well, the compilation failed, right? Let me see why. Okay, I think it actually went through. So the compilation actually went through. So next, we're actually starting the proof server. Now, like I said, the proof server is important. You need to run the proof server. If not, you're going to have issues. That's why you need Docker. Docker allows you to run a complete. Think about Docker. You probably know what Docker is, but Docker gives you the ability to run an entire suite of applications, a bundled application, without having to worry about integrity. It just like packages it, the working version, and you can just run it locally, right? Just going to run it. Docker is installed. We're going to run the proof server, and I think I have it currently running. So I'm going to do Docker ZLS or something. What's the command again? I can't remember. But I think I have my containers running. Probably need to stop it on the other version so that we can use it right here. Let me just stop it. All right, so I'm gonna do Docker compose down. I'm gonna do Docker. I'm gonna start this one. Boom. So now it's running. I had to stop a running a running container somewhere else in a proof server that I've running somewhere else. So now that I've stopped that, let's go deeper into this. I'm excited. Okay, so we have everything pretty much set up. Proof server is running, very important. We've compiled our smart contract, so the base project that we cloned actually works. Now we need to write the smart contract that we set out to write, which is the voting one. I think I have the very not so interesting diagram set up right here. So, like I said, what we're trying to build is a private voting system. You have all these very interesting fellas. I'm just gonna put A into them. A. Oh, by the way, I'm already revealing their identity, so ideally you wouldn't know who is A or B, C. So we have these young boys and girls trying to vote. You know, we want to take a very important decision. We want to vote between a yes or a no. But we don't want to know who voted. So like what we want to do is once A votes, we know that one person has voted. One person has voted, but we sort of don't know who that is. So let's say once B2 vote, let's say B voted for no, it moves over to the tally count, but we have no idea who that is. We just know that there's someone who voted for it. Then now let's say C voted for yes, and then somehow we can't tell who voted for yes. That's what we're trying to achieve. Hopefully that sort of makes sense right now. So with that very crappy demonstration, let's get into it. All right, like I said, now that we have a very a clean setup, let's start doing some renamings. And this is very important. I'm just going to zoom in a bit, just in case that doesn't look too big in the editing. And now I'm going to open the contracts. And this is the way compact is written. Once I open it, because I have that VS Code extension running and set up, if you see we have like the syntax highlighting, otherwise you won't get the syntax highlighting and all this nice color code that's happening. It should just be white. We don't want that. So install that VS Code extension, very important. So I'm going to create a voting contract. I'm going to come here, create a voting.compact. That's the first step. And you remember what we're trying to do is we are trying to write a private voting system. So I'm going to create this voting.compact, and then we're going to start writing our smart contract. That's the first thing we need to do. We need to worry about this. We can let every other thing rest for now. Okay. So how does any compact smart contract start? It starts with declaring the version of the language you're using. And if you're familiar with Solidity, you probably know this already, right? We start with pragma language_version. This is how you write it, right? And this tells us that use the compiler, the version of the compile language you are using is a version that is greater or equals to version 0.20, right? Very important. It's a safety check so that we don't accidentally compile with an older version, and in case new support has happened, so the code knows that, oh, there's a new feature we should be expecting. The compiler just makes sure we use the right version to compile the code. This line just makes sure we use the right version to compile the code. Very important. And then next, we're going to import some standard libraries, right? We don't want to write everything by hand. So what this will give us is, gives us a bunch of useful built-in tools like the counters, the maps, the Merkle trees, and some of the hashing functions that we need. And instead of building everything from scratch or writing functions and everywhere, we just use some of the provided things that compact gives us. And then next, we want our user to be able to vote yes or no, right? A user can vote yes or no. And Compact has a very strict system of typings. Think about TypeScript, where you have typings. It's very important in Compact because we want to make sure the data you're providing looks a certain way, is shaped a certain way, is expecting a certain type of input. Very important with Compact as well. So we want to define the number of options that a user can have. let's say the vote choice. We're going to call it vote choice. And the way we do that in Compact is something called enum. So think about enums as a way to create a fixed set of options that can be available to a certain variable. For example, we are creating a variable called vote choice, which is essentially an enum, and we are saying this can either be a yes or a no, right? Those are the two things that vote choice can ever be. It can either be a yes or a no. Any variable or anything that is exported in a compact smart contract is available when writing our TypeScript side of our applications, because a smart contract is deployed. There's a web applications that is either interacting with it or something with JavaScript or TypeScript that is interacting with the smart contract somehow, right? We're making this available in a TypeScript application. If you don't export it, it will just be something internal that can be referenced from outside. So we don't want that. Then next, we want to have something called phases. Now, I'm going to explain this a little bit. So we're going to have three phases. We're going to have a registration phase, we're going to have a voting phase, and we're going to have a closed phase. And phases is important so that we can track a registration. Voting starts, everybody should register, and then voting begins, nobody can register again, and then voting closes, nobody can vote again. So like 3 stages, 3 phases, different level of access and control. All right, so now that we've defined a little bit of the enums, let's talk about like states. In Compact, or when dealing with the Midnight network, everything is sort of like private by default. I mean, for a blockchain that with Compact, everything you create is private by default. So you need to declare when you want something to be a public state. And by public state, it means it will be visible for everybody to see. And the first thing we're going to declare is the creator. And we're going to make this a ledger. So anything you call a ledger is public, right? And the creator, this is a variable that will hold the address, the public address of whoever deploys the smart contract. And then, we're familiar with export, so I won't call it out again, but we're seeing a new type of instruction here. And this one is sealed. And what sealed means is that once you set this value once during contract initialization, like once the user deploys that contract, and we can set a value to this. By the way, this takes in a 32-bit hash, right? 32-byte hash. It means that this can't be changed anymore. So creator just becomes permanent. Once you set it, it is sealed. Can't change, can't delete, can't reshape. It's stored on chain. Then the next state we're going to deploy, or we're going to create is, what's going to type in here, is a proposal title. It's a ledger as well. And this is going to store the title of whatever we're trying to vote for. Another thing that we can also include is the proposal description. Proposal description, right? A title, a description. So, for example, a title can be, should we deploy V2 in March? And then people can say yes, no. Description can now go into detail about like what's important for people to understand about the voting proposal. That makes sense. Then this may be opaque string. I'm not going to dive deep into this part, but the maybe type means it can either have a value or it can be null. So it's either it holds something or it doesn't hold anything. So this can be empty and then later hold the value. Then the opaque strings means that this string is something that you can't read directly, right? It just means this can take any value, but they'll be rendered as string. Right. So if you put 1, 2, 3, 4, it is a string, becomes a string. That's what it means. Right. There's a lot more detail in the Compact documentation, which you can find in documentation. So if you want to the breakdown of everything, that's probably the best place to get that. Then we're going to deploy 2 counters. And the counters are like is a type. So we don't have to do increment, decrement, and all of that with manually, because that are some of the ways that you can introduce acts into your smart contracts. We'll just use the counters that we are provided by these guys, the counters. So we're going to create something to count the yes votes, something to count the no votes. So when somebody votes, we increase that particular vote choice by 1. So if somebody votes yes, we increase yes votes by 1, no votes by 1. It goes without saying. That's pretty clear. Then another thing to hold the face. And even though we define the enums, we need to also hold the face, right? And I think I made a mistake earlier by saying this is a variable. This is actually just an enum that just holds a type. So this can either be a yes or a no type. But this is the actual thing that holds whatever value this is. So we can say face is a type of face. And it means this guy right here, which is the variable, can either be registration, voting, or closed. This is the actual variable that holds the data, right? That holds the thing. This is just declaring what those things can be, the possible options of those things. That was a mistake, and I just fixed it. Then we're also going to declare the ledger for the voters. And this is a Merkle tree. And you can go deep into what Merkle trees are and whatnot. However, just a little breakdown. A Merkle tree is like a data structure that lets you prove something is in the tree without revealing everything else that is in it. So think of like a data structure where you can say this thing exists here, but you can't actually prove, you don't need to reveal every other thing in the tree. We can just find that specific thing and just prove that it exists in that tree. If you want more stuff about this, honestly, check out the compact reference. It's a really good resource, right? And then the historic part of this type means that it can keep track of the past states of this tree, right? Because history, past state of the tree, right? And then in this instance, we are creating a tree that has a depth of 10. So it goes as deep as 10th depth. And it can, with that, it can hold about 1,000 entries. And each of the entries is going to be a 32 bytes hash, right? Interesting. Compact is interesting, honestly. Once you get the hang of it, straightforward. And with the MCP thing, you can actually chat with the documentation. We're probably going to spin up a test for you to see. Then next thing is the export ledger has registered voters. We want to track if our contract has registered voters. If not, you will not be able to start the voting. We don't want you to start voting without having registered voters. This might just be like this one is an optional thing. I just felt to be cool to have without, because why would you start voting without voters? Then the other thing we're creating is a nullifier variable, and this is a set. And a nullifier in Midnight or Compact is basically a one-time token that you can use to prove that you voted. So think about like when you want to vote, you can have a nullifier that you can use to submit your vote. And we don't know we can't return. So we can like use the nullifier to identify who created it, but we can just know that, oh, you have to create a nullifier. So think of it like a token that proves that you are who you are without revealing who you are for you to vote. Interesting, right? And then you can also use to keep track of the state where, oh, a person has voted and a person has not voted. And now we'll go to another interesting part of Midnight, and something called witness. Now this one is pretty interesting, and I think you'll like it. So what is a witness? So you see that it looks like a function, right? It looks like a function. And honestly, a witness is an interesting concept. When I first looked at it, it wasn't really that clear to me, but I get it now. In Compact, a witness is a function that provides a private data to the contract. You know, in other smart contracts or types and everything, you probably have something called oracles and everything, right? With Midnight, you can use a witness to inject data from your front end into the code. And it's a function that you can run in your smart contracts that is not being declared in your smart contract. It's actually declared outside the smart contract. So in this instance, we are declaring the voter's secret. And this is going to be a 32 bytes value that only the voter will know, you that are voting. And it contains everything about their identity, their commitment, their nullifier. We use this voter secret to create and generate it. And it's a witness, right? It's a witness and it stays completely private, you know. Very interesting stuff. And then the other witness we're going to create is the voter commitment to register, right? And this is going to provide a commitment hash that the creator use when registering a voter, right? When you are registering a voter, you need to send in a commitment, right? All of this is done off-chain, by the way, like I mentioned. This is not declared here. It's done off-chain. It's going to be provided by the TypeScript code or whatever you're using to run it inside the smart contract. So a voter will compute their commitment hash on their machine. It's not leaving their machine. They're going to use some interesting, functions, create a commitment hash. You don't need to worry about it. You're going to say it. And it's going to send that privately to the creator. Right? The creator will now use that commitment hash to register that person on chain. Because the commitment hash is not the public address. So you don't know the address of the person. So you can't tie a vote back to them. But that for commitment hash is a constant thing that can always be generated and you can use to tie that the person has registered. Because notice there are three phases. There's the registration phase, there is the voting phase, there is the closed phase. In the registration phase, you need to submit your commitment hash. You are committing to vote, right? But you can't tie that commitment hash to the address of the person, okay? So you can't know who voted for what. So once you have the commitment hash, when you are trying to now vote, we have to confirm that you've registered. We're going to verify that using the commitment hash that this person has registered. So we're going to use this to get it. So the voter's commitment to register. So that's the registration phase. I hope that's really clear. And then the other part is the voters part, right? And this one is also when someone is trying to vote, we need to prove that they are in the voters tree without saying which entry or where they are in the tree, right? So this witness will look up the Merkle proof part, and then we're going to find their commitments on the tree, like, oh, this person is a voter, he has registered. Then when the part now confirms that the person exists there, this person is registered, we're going to know where they are. So practically they exist. That means they've registered. It's a very interesting concept with Compact and Midnight, because they're linked with zero knowledge proofs and all that stuff. By the way, Compact reference, check it out and also use the AI. I'm going to do a demo very quick, but not now. Let's keep going. Now we've gotten to, we've written out a bunch of the data types, and then I've tried to explain as much as I can to make it clear without going deeper into stuff. We're going to start writing some functions now. And in Compact, functions are declared using a keyword known as circuit. All functions start with circuit. So this is a derived public key circuit. It's going to take the secret key, right, of the user, and it's going to do a persistent hash, type of encoding on it, and it's going to return that, and that's going to be our public key. Right, it's going to derive the public key of the user from the secret key, and that was going to be, I think, we're going to store that for example, the creator. Now we need it for the creator, and wherever we need to get the public address for. Then there's also another circuit that we're going to declare, which is the derived nullifier. We're going to also use the secret key of the voter or whoever is interested in this smart contract to derive the nullifier, and we're just doing it a bit different. Right, this is going to be the private key. This is going to be the NUL. By the way, Compact reference, if you want to go deeper into this, we're going to use the persistent hash function in circuit. And that's why we also need to import all the standard library things, so we can use things like persistent hash and all of that without writing any of those code ourselves. Right. Then another thing we need to also declare is I think we have the public key, derived nullifier. We need to also be able to derive the commitment. And we're also doing all of this using this one is done with the public key, by the way, by deriving the commitment using the public key, right? So we're going to get the public key and then use the public key to get the commitment of the person. And then we have the constructor. And this constructor is this is the code that runs once you deploy the smart contract. And what's happening here? We're going to disclose who the creator is. So we're using the voter secret. There's a witness that is passed from the user to the smart contract, and we're going to derive the public key of the person, and disclosing it makes it visible, right? It doesn't hide it, doesn't do any interesting action of it, and we're going to store it in the creator variable and the public ledger variable we created. And a number of things are going to be declared as none, like this. For example, this one was a maybe. That means the proposal title can be present on deployment, or you can set it up anytime you want. So it does not have to deploy with a value when you're deploying, and a number of stuff. Setting the phase to registration phase. See, this was an enum. So the way we deal with enums, we can do phase to registration. Then as registered voter was a Boolean, and now we're declaring it as false. So when you're deploying, of course, you're starting with 0 voters. So once you have registered voters, we're going to make that true. Then we're going to create a circuit. Like I said, a circuit is a function that you call in Compact. Remember, these are two different types of circuits. This circuit does not have the export. That means this can't be called outside of the smart contract. It can only be called internally. And then there's this one with the register voter. By the way, this is how you now call it on your front end or your CLI, because as exports, you can actually call this outside the smart contract, right? The export is there. And the TypeScript will be available for your outside application to call. Okay, this calls and registers the voter. We can go into the details of how it works. I'm just going to get all my circuits in there. I'm just going to get all my circuits in there for us to get started and close voting. So I've pasted all the circuits in, right? We have the one that will register the voter. We have the one that will start the voting. We have the one that will actually do the voting. Like, so you can say, oh, I want to vote a yes or a no. This is the one we'll call to do all of that. And then the one that will close the voting. So let's quickly skim through what's important in them. Register voting, we get the commitment. And we're going to just store the commitment of the user to know that, okay, we have somebody's sending in a commitment to be a voter. They've not voted yet. And so we also say, oh, do we have registered voters? And that's true. And by the way, we do a number of checks. Only the person that deployed the contract can actually register a voter. For example, if you try to register a voter without being the creator or the deployer of the smart contract, you're going to get this error saying only creator can do this. Then also we need to be in the registration phase. The way we do that is using these assert checks. You're going to see assert a lot because that's the way we can do like allow this, don't allow that. And the number of the things that we're doing here. Close voting so as well. We are using the witness for the secret key, and we're using it to make sure that the person that is doing the closing votes function or circuit is a creator, and other options right here. So now that we have our smart contract written out, you can go deeper into this, use the AI to explain. Let's actually compile our smart contract and deploy it locally so we can test. And the way to do that is you go to package.json. You need to change the number of things. For example, we're no longer referencing hello world, so just change all of this to voting. Everything you can change to voting, change it, right? And now let's do compile right here. So it's going to try to compile the smart contract. Let's see. And then once all of that is compiled, boom. So we see no errors. Our smart contract has successfully compiled. I'm really excited for this. Okay, now that we have a successful compilation, let's go ahead and deploy the smart contract. To do that, I'm just going to run npm run deploy. And you have to check your deploy scripts. The code to run right here. You see npm run deploy is going to run the deploy scripts. You can either create a new wallet or restore from seed. So that's the way the CLI front end works in Midnight. You either create a new wallet right there or you restore from a previously generated seed. I like to use the seed version because I have previously funded a wallet address. All right. If you're doing it for the first time, you definitely don't have a seed. So you choose option 1, you smash enter, but I'm going to select option 2 and then paste my seed. That is because I already have a seed. In your case, if you don't have a wallet, select option 1 and you will get a seed and it will generate the wallet for you. And then because your wallet would be empty, like no tokens at the start, you will need to get tokens. And I think I showed you how you do that. You need to go to the faucet. In the README, you should find a link to the faucet. You find a link to the faucet, right? If you go to this URL, you can paste your wallet address and get test tokens so you can play around with deployment. Right, so we did all of that. My character seed has been pasted and my wallet address was generated with that seed, right? This is what you copy and paste in the faucet. But I already have like some balance. You see, I have about, I have some T9 tokens right here. And I went ahead to try to deploy the contract and boom, the contract was deployed locally on my machine. and stuff was saved into a file called deployment.json, right? And this will be used for other stuff later down the line. So it's just a way to preserve the contract address without having you to do it multiple times. Okay. So that is a successful deployment. Our contract was compiled. Our contract has been deployed. The next thing to do now is to now play around with the smart contract features and see if they actually work. So for that, we're going to do npm run CLI, like the instruction says. And that will start the front end that we've built. So think about the CLI like a front end testing thing without using the browser. So we've written code. I'm going to share this in the GitHub with the project, so you just run it locally yourself. It's a lot of code, so you can go through it one by one, and you can use the Midnight MCP to explain what you need. But this is not focused on writing that front end, so that's why we're going to skip all that part and just test. Once again, I'm going to paste my seed so that we can connect to the pre-prod environment, and we can go from there. It has connected successfully to the Midnight pre-prod environment. Our wallet has been synced, providers, everything is up, and our CLI is actually running. And with the way the CLI is written, we can see we have DOS tokens, we have our face showing the faces, and we're also showing the tally of the votes. So as a creator of the smart contract, you see more options. The way the CLI is written, you see more options than any other person. So you can register yourself as a voter. You can register other voters. Then you can start the voting, which will change the face from registration to voting, remember, from the contract. And then you can close the voting, which will change from voting to closed. Then you can also vote yes or no. If I try to vote right now, you'll see that we're going to get an error. So just testing a bit of things. Right now, this will throw an error saying voting has not started. And that's because we need to explicitly start the voting process. So voting is not open. That's because we are checking if the registration phase is in the voting stage. So voting cannot happen right now. Now, as a creator, you can also register yourself, right? Or register other voter. For this example, we're just going to do just the creator. Let me register the creator self. And this will take about a few seconds. Self has been registered. So you've registered yourself as a voter. And this is the transaction ID for that interaction on the blockchain. Now we need to start the voting process. I can still vote because the registration has not started, but we now have someone registered. Let's start the voting process. So if I select option 3, we're going to create the proposal title and also like the proposal description. So should we deploy prod? And then this is important for the description, right? This will create the proposal title and description so that we kind of have something to vote for. All right. Now we have voting proposals. We have a proposal we can vote for. See, proposal, and the face has successfully switched to voting. Vote now started, transaction ID generated, and now we can vote. So as a creator, I'm going to vote for 4. And this will execute cast that vote on the blockchain. And if everything works, we should get a successful vote right now. The vote has been casted, the transaction ID and everything generated. And you see that the DOS tokens has reduced a bit. And we now have 1 voter. The way this voter happened is we can actually tell who owns that vote. We know that there's a vote. We know that one person has voted for yes, but we can't tell who made that vote. You can go to the contract to see all the process once again to refresh your memory. And that's how you build a private voting system with compact and deploy it on Midnight. We went from setting up our environment to writing a smart contract and also deploying on Midnight locally. And I also mentioned about the Midnight MCP a bit. Just play around with it. It really works because you're in Cursor, you can chat with your agent and get really great help indirectly in your IDE. And that concludes everything. If you have questions or you have something you're trying out, leave them in the comment section. Otherwise, you can create it in the Discord for the Midnight community, and somebody will definitely answer you and help you with your inquiries. I look forward to seeing you on the next one.